Hey folks, so this is a video lecture discussing some of the ideas from chapter 6 of our textbook. So these are topics surrounding inner products and distances or lengths and orthogonality. Now, unfortunately, we didn't have time in class to go over this together, but I wanted to give you at least some of the basic ideas in this video for those who are interested. There's just so many cool nuggets about orthogonality that, it felt a shame not to share some of these cool ideas with you. So the motivation is going to be the following. So when I think about a basis of R3, for a lot of us, this basis comes to mind, the standard basis, right? And the standard basis is great, but is it really much better than some other random basis? Is it just that it's more convenient, or is it truly better in some mathematical way? I mean, we know that both of these bases span R3, they're linearly independent vectors. I mean, that's all has to be the same. But what is it about the first one that makes it easier? And are there other types of bases like this that are equally, quote unquote, easy to use compared to like a random basis? And what does that all mean? So to answer these questions, we're going to introduce what's called orthogonality. It turns out that's the key way to understand why some bases are a little bit better than others. So to do that, we'll start with what are called inner products. So what's an inner product? It's a way of multiplying two vectors together. Now, we've done a lot of matrix times vector multiplication, matrix times matrix multiplication, but we haven't done vector times vector multiplication this semester. It turns out it's possible to do a couple of ways, but the one we care about is if I gave you two vectors, u and v, I want to think about the product u transpose times v. Now, let's think about what that is. So u and v are both column vectors. So if I do u transpose, it becomes a row vector. So this is my u transpose. And then v by itself is still just, well, v. So that's my v vector. And notice if I were to multiply these two things together, I get a perfect pairing between all the dots, right? And my answer is going to be a single number. Now, that's really nice. This specific product of these two vectors is called the inner product or the dot product. You may have seen this terminology if you took a multivariable calculus class. Yes, this inner product or dot product. So just writing down a formula for this, right? So if my vector u is given by u1, u2, and so on, v is v1, v2, and so on, then this inner product, this dot product, is the sum from I equals 1 to n of ui times vi. That is, you take the first number in the vector of u, first number in vector of v, multiply them, second number in u, second number in v, multiply them, and do that for every pairing, and then add up all those answers. That's it. That's the dot product. Now we have a couple equivalent notations. It's typical to write either the dot between them to say this is the dot product, or you use these sort of angular brackets to say u inner product v. Okay, but it's all the same thing. It's the specific way of turning two vectors into a single number. So for practice, let's go ahead and calculate an inner product or a dot product with these two vectors here, u and v. So if I'm doing u dot v, then I'm going to look at the first component of u, 2, times first component of v, 3, plus second component of u times second component of v, plus third component of u times third component of v. So if I add this all up, it's 6 minus 10 plus 3, which is minus 1. And as we hope, right, the answer is a single number. And just for good measure, right, you might notice what's going to happen. But if I were to compute, instead of u dot v, I compute v dot u, you might notice that I get, oh, well, it's 3 times 2 plus, okay, 2 times minus 5, okay, plus minus 3 times minus 1. But, if you compare this to the stuff above, of course, you're going to get negative 1 again. And so what's kind of nice about dot products, although in general, we're very worried about switching the order of multiplication of matrices, right? In this case, inner products have this nice property that u dot v, v dot u are exactly the same. So you are allowed to commute inner products or dot products, which is really nice. It's a nice property. It's a little bit surprising considering how much of this class we were not allowed to do this. So it's kind of nice. So what is the point of inner products? Like, what do we use them for? It's kind of a random calculation, right? Well, it turns out it tells us a lot of new things. So one thing it tells us about is the length or norm of a vector. So let me write down a formula for you. So if I give you a vector v, then I put these double bars around it. That's the symbol for length or norm. And it's going to be given by the square root of v dot product with itself. And you might say, well, that's a very strange formula. What does it have to do with length? Well, let me give you a specific example to show you why this should be the length. It turns out inner products are very closely related to length in the following way. So if I gave you a vector v, which was, let's say, v1 comma v2, then let's see what happens when I plug that into this formula. It's the square root of, well, v1, v2 dotted with v1, v2. So dot product with itself. And what do I get? Well, it's the square root of, again, v1 times v1 is v1 squared. That's my first component, plus second component's v2 times v2 is v2 squared. So I'm going to add that. And maybe written this way, it looks a little bit more intuitive for us, especially if you've seen a multivariable calculus class. This is the formula for the length of a vector, which you could see geometrically as the hypotenuse of, right, sort of this right triangle with components v1, v2. So this is the length of the vector, as maybe we're more familiar. So it turns out that, yeah, this comes from an inner product definition, which is kind of cool. All right, so fine. So inner products tell you about length. Does it tell you anything else? Well, yes, it turns out inner products will also be helpful in helping us understand orthogonality. So what is orthogonality? To motivate it, let's do an example. So I have this vector u, which is the vector 1, 2. Let me go ahead and draw that. So it's 1 across, 2 up. Here's my vector u, 1 comma 2. And so my goal is to find a vector perpendicular to u. And so how do I do that? And I give this hint, maybe it's useful to think about slopes. So what would the slope of this vector u be? Well, it's sort of like the rise over the run, right? And so this is 2 up, 1 across, so 2 over 1 would be my slope. Okay, and you might remember some facts from like some earlier algebra classes that a perpendicular slope would be the negative reciprocal of this. So perpendicular slope wouldn't be 1. It would be not, 2 over 1, it'd be negative 1 over 2, so negative 1/2. And so that gives me the idea of, well, if my original vector was 1, 2, and I look at, how that turned into my slope, maybe I could take this new slope and turn that back into a vector, sort of doing the thing we did with 1, 2 in reverse, right? So let's turn this negative 1/2 into a vector. So that should be the vector, what, 2, negative 1. So if I look at the vector 2, negative 1, looks like something like this. 2, negative 1. And I mean, at least from the picture, it's pretty conceivable that this might be a right angle. So, okay, I think we've accomplished our job, but you might say, like, well, what's the point of this example? Why do I care about this? Well, just for the sake of interest, let's take the inner product of these two vectors. So 1 comma 2, inner product or dot product with 2 minus 1. And what do I get? I get 1 times 2, which is 2, plus 2 times minus 1, which is minus 2. Oh, I get a 0. Now, it turns out that this is always going to happen. So this is the power of inner products. That is, if two vectors are perpendicular, their inner product should be 0. And that's how we define orthogonality. Orthogonality is a way of talking about perpendicular vectors. It's really just kind of a synonym for perpendicular. So two vectors u and v are orthogonal or perpendicular if their inner product u dot v is 0. That's it. Okay, so orthogonality gave us now length and also a notion of perpendicular. Awesome. So let's take it home. The takeaway of this is, well, what if I give you not just two vectors, but a bunch of vectors? We're kind of getting ourselves towards basis, right? So if I gave you a set of vectors, v1 through vp, then we say that whole set is an orthogonal set if every single pair of vectors is orthogonal. Okay, so I have to check v1 against v2, v1 and v3, v2 and v3, and so on, right? Check all of these distinct pairs and make sure that they're all orthogonal from each other. Let's take a good example that we know, like the standard basis, right? So if I gave you 1, 0, 0, 0, 1, 0, 0, 0, 1, the standard basis of R3, this is an example of an orthogonal set. And you could check by saying, well, take any two of these, 1, 0, 0, dotted with, let's say, 0, 0, 1. And if I dot product these, you get 0 plus 0 plus 0, which is 0. Yeah, so those are orthogonal. Now, technically, you need to check every pair of them, right? But if you do, no matter which pair you take, they're all going to dot product to 0. Everything is mutually perpendicular. Awesome. Okay, so we have an example of an orthogonal set. Why is it so nice to be an orthogonal set? Well, the takeaway is the last two theorems that are written here. So first, it turns out that if I give you an orthogonal set of vectors, then it is automatically a linearly independent set. That's kind of nice. So orthogonal implies linear independence for free. This is actually a beautiful, beautiful proof. I really enjoy this proof. So I'm going to save that for another video after this one. But for this, I want to give just the main ideas. So I'll skip that for now. You take it as truth. But I wanted to at least give an intuition for why that theorem should be true. And the intuition is, well, just think about like R3, right? If I give you an orthogonal set, then you're thinking about sort of three vectors that are all 90 degrees away from each other, right? Every pair is a 90-degree angle. So like this is a 90-degree angle, and this is a 90-degree angle, and this is a 90-degree angle. So because of that, they're all sort of forming different directions. So they all point in different directions. So they must be linearly independent. Okay, that's the idea. If they're orthogonal, then they must be linearly independent. Awesome. Okay, but a regular basis already does that. So why is an orthogonal one even better? Well, that's summarized in this final result, this final theorem, which says, if I gave you an orthogonal basis for your vector space, that is, it's a basis that happens to also be orthogonal as an orthogonal set, then for every vector in the vector space, we can write y as a linear combination of that basis. Well, that's not surprising, right? You already could do that with any basis. But the point is, for an orthogonal basis, there's a formula for it, right? In general, to find the coefficients that give you this linear combination, you have to sit down and row reduce, calculate some stuff. But no, for an orthogonal basis, finding the unknown coefficients is as simple as take your vector that you want, y, dot product with the ith basis vector, divide by the ith basis vector dotted with itself. That's it. You calculate that for every coefficient, and you're done. That's your linear combination. So that's why I love orthogonal bases. They are much simpler to use if you want to find, for example, linear combinations. So last thing in this video, let's do an example. So I'm going to take the vectors u1 and u2, and I want to write the vector x as a linear combination of these two vectors. Now, of course, you could do this by the way we did it back in chapter 1, write a matrix, augmented matrix, row reduce, find the coefficients. But instead of doing that, I notice that u1 dotted with u2 is 2 times 6 plus negative 3 times 4, which is 12 minus 12, 0. So u1 and u2 are orthogonal. So u1 is orthogonal to u2. which means I can use my theorem above, right? Because these are now linearly independent and thus a basis for R2. So I can use this theorem to calculate this linear combination coefficients lickety-split. Let's do it. So I want to write X as a combination of some amount of U1 plus some amount of U2. Then I can do it by saying, well, C1 is X dotted with U1 over U1 dotted with U1. And so like up here, X dotted with U1, it's 9 times 2, which is 18, plus minus 7 times minus 3, which is 21, over U1 dotted with itself. So that's 2 times 2, which is 4, plus negative 3 times negative 3, which is 9. What does that give me? 39 over 4 plus 9 is 13. 3. C2. Same thing, but I'm going to use U2 instead. U2 dot U2. Again, a little bit faster. X dot U2 is 9 times 6, which is 54. Minus 28, that's negative 7 times 4. Over, now U2 dot itself, 6 times 6 is 36. Plus 4 times 4 is 16. And okay, well, I got to be careful now. So 54 minus 28, that looks like it's 32. Over 36 plus 16, that's 52. Did I do that right? So 54 minus 30. No, okay, I think it's right. Yeah. No. Something here doesn't make sense. Addition on the fly. 54 minus 28, right? So 54 minus 28 should be a 6 and then a 26. Okay. Careful with your algebra. Yeah, that's how they get you. All right, 26 over 52. That looks like a nicer number, though. That's a 1/2. Okay, so then, assuming you can do your arithmetic correctly, we're now done. There's my linear combination. 3 U1s, 1/2 U2s, I'm done. And again, if you don't trust me, you could go back and actually just calculate, right, all of these, right-hand side coefficients, multiply by u's, and see that you get x back out. All right, so hopefully this was informative. I will go back and make another video on that proof of that theorem that I skipped, but this gives you at least some of the introduction to what are orthogonal vectors, why do I care about orthogonal vectors, and hopefully you're convinced that orthogonal vectors, orthogonal bases, are really, really nice ones. Okay, if you have any questions, let me know.